on the elements that are in a given consecutive positions, we don't disrupt what that reduces to, the pattern that occurs there. So what we can do is we can start at position k plus 1 here and build out to the right using the first n minus k of our sequence of x's. Then that will be a Mallows permutation with parameter q of that length. Then we can reverse it. If we reverse it, we have a Mallows permutation with parameter 1 over q, but we can build then from right to left, so we build back to the front, and so then we're left with a permutation of length n that has parameter 1 over q, and we can reverse it back again, and all the while we've left this part intact. Okay. So with all those properties established, I'd like to ask, what's the probability that a Mallows permutation avoids some pattern consecutively? So this property does not hold in general for general Q, so it's a bit harder, maybe impossible to say something about Mallows for classical avoidance. But I'll talk about consecutive avoidance in general. So let me just specialize to that case here. So suppose I have some permutation of length 6, say. And I'm talking about consecutive avoidance for the pattern 1, 2, 3, something small. Then in order to determine whether the pattern occurs consecutively, all I have to do is I scan these consecutive, or each of these locations, and I can check whether or not the pattern occurs in that location. So in general I define, so for general permutation sigma and pattern tau, I can define random variables yj, where yj is going to tell me whether or not the pattern tau occurs starting in position j as a consecutive pattern. Okay, and so if one of these occurs, the pattern occurs, and I can calculate the probability that a pattern occurs in this location by using the homogeneity property. The probability is the same for all locations. It's just given by the Mallows distribution applied to the pattern tau. And so what I'd like to do is I'd like to estimate or somehow approximate the number of occurrences, which is the sum of these yj's. So this is the number of occurrences of tau. And let me define lambda to be equal to n minus k plus 1 times p. Okay, so this is the sum of these p's. It's the expectation. It's the expected number of occurrences. And I'd like to estimate the probability of avoidance by e to the minus lambda. So that's the probability that a Poisson random variable with mean lambda is equal to 0. And so the question is whether this is a good approximation. And even more generally, I'd like to ask whether I can approximate the number of occurrences by the Poisson distribution. Okay. And the way to assess the quality of this estimate is through the total variation distance, which is given by So the total variation distance between two random variables is the sum of the absolute differences of the probability masses. So, in order to apply the Poisson approximation, I need to...
This is for Mallows or finite form?
I'm going to talk about a little bit about both. Yeah. In order to apply the Poisson approximation, as I mentioned earlier, I need lambda to be a moderate size. I need the number of occurrences to be relatively small, because and this is why we consider large patterns, okay, patterns that are large relative to n. So one of the questions that we're interested in is how big does that have to be? Did this turn on?
You do it right now. Yeah.
I should push it again?
Yeah.
So if we didn't let tau grow, then what would happen is the expected number of occurrences would continue. Is this still on?
Yep, that's coming right now.
The expected number of occurrences would grow indefinitely as n gets larger, and the probability of avoiding a permutation would be negligible. And the hope of getting a reasonable approximation, other than the probability is 0, is no good. And I think that for that problem, isn't that related to something that you've done with Brian Nakamura and Svante Janssen, where you count the number of occurrences and you get some central limit theorem, right? So in this case. And so the central limit theorem is telling you what the center of the distribution behaves, and doesn't give you the thing on the end, the probability of avoidance. And so in this case, this is where the sheet may be helpful, and I'll just advance by this. So this is the theorem on your sheet. This is just a theorem that we're going to apply in this setting to the random variable that we have up here. So it's a pretty powerful technique, because this is a valid calculation for any sequence, any collection of random variables x alpha. So these are indicator random variables. So take the values 0 and 1. They can have arbitrary dependence, and these bounds are always valid. That doesn't mean that the bounds are always useful. And actually, what I have up here on the slide is you have a more general version on your sheet, because there's an additional term, B3, that it doesn't come into play here, because B3 is equal to 0 in our setting because of the dissociation property. So the tricky part about this is that we have to take account of the overlaps. So if two locations overlap, then there's some dependence among these random variables, but by the dissociation property, if there's no overlap, they're independent. So there's some local dependence that's going on here that is enough that we can handle, and so we get these bounds for the probability of avoidance, and in general for the total variation distance. So just applying these bounds just applying this theorem without thinking any further, we can calculate these bounds, and we can calculate these two quantities, and we get a bound on the number of permutations. So here, this is just the case of the uniform case for classical pattern avoidance. So not consecutive avoidance. So we see that the number of possible subsequences is n choose j, and each has probability 1 over j factorial for a pattern of length j. And so we can count these, and the only thing that, for an arbitrary pattern tau, the only thing that's hard here is the fact that we have to count how many ways there are for the pattern to occur in two overlapping locations simultaneously. So sometimes that's impossible, and sometimes it's not. And so in general, we have no general. We can't give a generic form for this sum. but we get these bounds, and these bounds are true. Although I'll show you in a bit an example where they're not always so informative. And here's just a case of consecutive avoidance, where I'll just use this notation with a bar to mean that I'm talking about consecutive avoidance, and we do the same thing. Okay, so this is the uniform case that I'm talking about specifically here. And so, as an illustration here, we have the lower bound given by this application of the theorem for certain values of n and certain patterns of length j. So if j is smaller than what we have up here, the bounds are not very good. And even this isn't great because I haven't listed the upper bound because the upper bound is bigger than n factorial in these cases. So we see that the lower bound is on the order, at least it's on the same order as n factorial, but that means that the error is also on the same order. So the question is, how can we, so how big does j have to be to tighten the bound? So what we find is that in the case of classical avoidance, and there's some asymptotic work that has to go into figuring out what's a big enough length to make those bounds b1 and b2 go to 0 with n. And we find that if it's bigger than roughly n square root of n, so we have e times the square root of 2 times the square root of n, which is the best we could do, but I think that the square root of 2 probably shouldn't be there. Then we get a valid approximation for all, and this is true for all finite values of n, and this is, so we get this approximation for the number of permutations avoiding a pattern of length j, and we also get a Poisson approximation. And in the consecutive case, we need j to be so that j factorial is bigger than n. Okay, that's big enough to get the approximation. Okay. So just to illustrate, so how good is this approximation? In the case of consecutive avoidance, and here I'm still talking about the uniform distribution. So I'll take the pattern 2, 3, 4, 5, 6, 1. So that's a length 6 pattern, and I consider consecutive avoidance in a permutation of length 6 factorial. Okay, so of length 720. Okay, and so by the previous theorem, this should give us, we should have a pretty good approximation from the Poisson distribution. So simulating from this 1,000 times, and here are the empirical frequencies. So the number of occurrences of the pattern and the empirical probability, which is the frequency out of 1,000, the number of times it's occurred. And comparing to the Poisson, the red x's are the true Poisson distribution with mean 1. Okay, so it appears to match up pretty well. And the total variation with the empirical total variation distance here is about 0.02. And you can compare that to what was given by the theorem. The theorem's a bit conservative. It gives 0.07. And finally, just to finish off, since I talked a lot about the Mallows distribution, and there's a lot going on in the Mallows distribution with this extra parameter q. We can now keep the pattern fixed if we like, and instead consider how q can vary in order to get a reasonable approximation. So there's various regimes that we can consider. We can also consider letting the number of inversions somehow vary with n as the pattern grows. And so there's ways to do this by, and I'll show an example on the next slide, where we keep the pattern fixed and we let q vary. So we can either let q be large or q be small. And if it grows along a critical region, or along the exact equality here, then we get what we show here. So this is the case where, so this is just the example where we have a pattern, two patterns, one of length 4 and one of length 5, and I'm letting Q grow here according to these, at these rates, and these are the rates given by the previous theorem. So we can either let Q get big or Q get small, and the solid line, which may be hard to see, the solid line is the approximation that's given by the Poisson approximation, and the dashed lines are the error bounds. So the dashed lines in this case are right on top of the line. So in this case, the approximation is very good. This is just an illustration. In principle, this can be applied for any pattern, provided that you can verify the conditions. Or otherwise, in the previous theorems, if you could calculate this overlap, then you also have maybe a way of getting an even better bound. So there's more details on this in this paper, and I think I'll stop now and I'll take any questions.
We have a couple of minutes for questions. I have a comment. The collaborator, Di Salvo, is speaking here later.
Oh yeah, in about a month, right?
Yeah. Because we're going to talk about something
Different. Something different. Yeah.
So it's, Brian Nakamura and other people did some explicit things for consecutive patterns. Can you compare for small, like, can you compare your result to the explicit things, or more or less?
So I tried to do that, but that was for fixed patterns, right?
Yeah.
So we're working on that right now with DeSalvo and also Sergio Elizalde, using some of those techniques to see if we can do some kind of get some information about the growth rates of these probabilities. Yeah, but that's ongoing. Yeah.
One question, is there any application where this is motivated? Where does it come from?
The question of pattern avoidance, or in
particular in this way how you define it, that any reduction of a certain length avoids a certain pattern.
Well, I personally don't know what the applications are. I mean, I was introduced to it through this seminar, and a lot of people study them here, but maybe Doron would know better.
No, in computer science includes
Right.
motivations for small patterns, and that is interesting.
So sorting, sorting algorithms was the first one.
Okay.
It would seem that this is applicable to card shuffling, just like that. I mean, because that's one of the problems. Nobody knows a good model for casino card shuffling. I wonder whether
It's possible, but everyone hopes that the distribution is uniform, right? But I don't know. I mean, I don't know if all models, if this one is right for comparing.
But card shuffling, there are models for card shuffling, which are permutation models.
Oh yeah.
A Raffle shuffle, which is different from uniform, very much different.
Harry will be glad to answer more questions if I will. Thanks again.